Okay. Okay, thank you very much, Luca and Francesca, for having me here today. It was not until Sunday that I realized that the title that I chose for my talk was far too ambitious. I don't do drugs, so maybe it was an overdose of pesto. I don't know what exactly I had in mind when I wrote this title. So I decided to change it and to make it closer to what actually I'm going to talk about. Someone said that science, research, is 10% inspiration and 90% perspiration, okay? How many of you are PhD students right now? Good number, right? So you know about perspiration, right? Perspiration is failed attempts. Is you try something, you think you had this great idea, or your supervisor had this great idea. He thinks it's a great idea, usually, because he's the supervisor, but he doesn't know really. I mean, and so you try it, and you fail. And failures don't make for papers, right? And it's publish or perish, and then you sweat a lot. And this talk is about sweating of many people, including me. My picture was taken here. I had exactly the same shirt, as you can see. This was different. I think it was the first year of this event. And there were many others that actually didn't even fit the slides. Someone I forgot, and I apologize for that. So what you're going to see is not my sweat, and not even my inspiration sometimes. So it's work by many people, and I thank them for accompanying me in this adventure. Okay, so this is the agenda. After all, the talk is going to be about formal assessment of complex systems, and a little bit of introduction. Actually, the talk that preceded me, especially the talk by Professor Carlucci Aiello, wonderful talk, but also wonderful introduction to the topics I'm going to discuss. So I'll be able to focus on the technical details. And in particular, some applications where we tried to be formal and survive, possibly with some good results. And finally, some conclusions, okay? I try to be cinematic here, but it's just for the fun of it. Okay, so what's our beauty? Okay, it's formal methods. And since I'm an engineer, I'm not talking about pencil and paper. Also, pencil and paper proofs are nice, but I'm not a mathematician, I'm not even a computer scientist, I'm a computer engineer. So for me, formal methods means something that you can formalize your system with and then have an algorithmic way of digesting this formalization of the system and of the properties that you want to be satisfied, and then extract some useful results, okay? It could be theorem proving, if you are a fan of logic, okay? So it could be interactive, it doesn't need to be fully automatized, or it can be something more push button, like model checking, where you have the system and the properties, and the model checker gives you a counterexample, or it tells you that the property is satisfied. It can be decision procedures, like for propositional satisfiability, for theories, okay? Or it could even be static analysis, whatever, okay? I did not mention testing, although I worked myself in testing quite a bit. My interest is more into automated test generation, because you can have an array of people just out from the university generate tests for you. If you thought that PhD is hard, think about your colleagues writing testing in the industry. It's harder and less rewarding. But in fact, you could also consider testing, as long as you do some kind of formalization, okay? So any method that allows you to formalize the system and automate the answer from a machine. And this is important because, as Professor Carlucci Aiello said, the systems are becoming more and more complex. even the system that we are using today are far beyond our capability of understanding them, of checking them, so we need other computers to be the computer, right? So we want system to check our systems, and possibly with a good understanding of what's going on. That's why being formal is important. Who's the beast? Well, the beast is what was called cyber-physical system, what I call complex engineering system. It's something that is cyber-physical, so it is a digital part and the physical part, and they are interconnected. The digital part actuates the physical part through actuators, and the physical part is read through sensors into the digital part, which takes decision and so on. It could be a robot, it could be something more complex. It's socio-technical. It means that the human is in the loop, on the loop, in control of the loop, somewhere around them. Usually humans are more of a nuisance than a value, okay? Think about autonomous driving. You are not worried when you go to an airport, there are a few of them, and you board a railway transit system, one of those internals. Do you see a driver? No. And you are fine, because it's a railway. It goes from A to B, maybe to C. There's no one else joining in at intersection, overtaking you and then stopping in front of you, or any other maneuver that I observe as a cyclist in Genoa. Yes, I do cycle in Genoa and I do formal methods, so I'm a crazy person. But you'll see that this is actually what happens. So if all the cars would turn autonomous, okay, suddenly, then it wouldn't be much of a problem, because as Professor Sangiovanni Vincentelli said, they would communicate with each other. May I pass? Yes, you can. No, they wouldn't be driving in Genoa or in Rome. As a Genoese, I have troubles driving in Rome. I don't want to think what an American would do, given the size of the street and the general politeness that is usually observed in the US. So, but humans are there, right? Until machines will eliminate us, or aliens, who knows, we are there, and we must take that into account. Systems are not built monolithically. They are far too large to do that. So you take commercial off-the-shelf components. Okay, and if the guys that design those components and build those components were not ethical, okay, you have a piece of junk in your system. Your system might be perfect, but that piece of junk is going to fail it. And somehow you have to take that into account. They are connected, also inevitable. Davide before was mentioning automation system. Long are gone the days in which automated systems were offline. You can still find them, like wastewater, there are still in some parts of the world some systems which are not connected on the internet, but the tendency is to get everything connected. And that enlarges the attack surfaces and makes more room for us humans to do damage. And finally, but not our least concern, the systems are complex. What do I mean by complex is that the total is more than the sum of the parts, right? So there are some behaviors that, like safety or security, that cannot really be assessed at design time unless you follow a strict discipline, because they emerge once the system is running. Sometimes you even go for emergent behaviors. If you talk to people doing swarm robotics, they love emergent behaviors, right? But unfortunately, they are not able to engineer them. They just run the robots in the simulator, say, oh, my robots are flocking. Yes, but can you ensure that? And that's an open question, as far as I know. Okay, so now there's the beauty and there's the beast. And the question is, will we have an happy ending? Or maybe not, okay? So clearly this depends not just on our ability, on our courage, on our passion, or our perspiration, but it depends also on the beast, okay? Because there are beasts which are kind of difficult to tame, as the movie Alien proves quite clearly. Okay. But we are all fans of Disney rather than Alien, so let's get down to business. These are 4 applications that I've been playing with in the past 10 years or so, together with many people, as I said. I'm not talking about what I've been doing in Cerbero, because you heard probably a lot from Luca and Simone. And also, I'm skipping some of the work I've been doing with the Italian Institute of Technology, which was more related, as I said, to testing or learning software in order to do verification, okay? But if you are interested into that kind of stuff because you saw my DBLP and you find some funny entry, I can talk about those offline. Okay, so these are the 4, and as the Fantastic Four, as the famous cartoons, each of these domains has its own characteristics, okay, which makes it different from the point of view of the application of formal methods. Okay, let's start with system monitoring and maintenance. What do I mean by system monitoring and maintenance? Well, first of all, the system can be very diverse. In my experience, I cut my teeth on networks of multimodal terminals. By the way, the network was never realized in practice. It was just prophesized, but the prophecy never came true. I've been dealing with locomotives, trains, and also stuff like HVAC units, heating, ventilation, air conditioning. Okay, so the system can be very diverse. So how you do go about formalizing such a system? Well, there is not really much you can do, but every system generates data, and you'll have to collect data. How do you collect data? Well, for several reasons. Since we are the formal guys, we thought that ontologies might be a solution to this data integration problem. So essentially, the first problem you have a system generating data, you want to integrate it in some formally well-founded way. If you don't know what an ontology is, don't worry, it's not really important. If you know what a UML diagram is, okay, then you know what an ontology is, in the sense that at the very basics, an ontology will allow to represent not just relations between the data, like a relational database, but also taxonomies, okay, like a GIS, a geographical database. So in fact, ontologies have this peculiar ability to be able to represent relationships, and many kinds of it, and also taxonomies, which makes a good compromise for a system where you have all these whole-part relationships. Also, ontologies are formally grounded, and when we started working in this kind of projects, they were also fashionable. Ever heard talking about the semantic web? These days is not as fashionable as the neural nets, right? But I can assure you that 10 years ago or something, maybe 15, the semantic web was really on the mouth of everyone. So much on the mouth of everyone that there was this railway project, okay, where they wanted to use ontologies in order to provide data integration for all the railway operators across Europe. It was a very ambitious project, and in fact it didn't work. Okay, if you don't see ontologies in trains, it's because it was not a great idea. The point is, ontologies are good for data integration. I'm not arguing against ontologies. If you are a fan of ontologies, please don't beat me outside. Ontologies are good, are fine, I love them. The point is that they are not good to reason about the system. So you can use them to integrate data, but once you need to reason about this data, you need to use something else. The only thing that ontologies will provide you is, for instance, if you try to attach inconsistent data to a model that you have previously drafted. So if you have a data model and the data that you're trying to pour inside the model is inconsistent, at the expense of running a description logic theorem prover, which is itself expensive, you'll have your answer. But don't try this at home. We tried. We of course succeeded to publish a paper because you always want to say something in the end, but it was not a good idea. Where it was a good idea, 2 other works that we have done, and you'll have it here if you want to browse them. In the case of monitoring this network of multimodal terminals, we used ontologies for data integration. So the point was integrate data, query the database to calculate some KPIs external to the database. And this worked. Also, we had this system where the software system, where the actual system was described using an ontology, and the rules to diagnose the system, to monitor and diagnose the system, were compiled using a data flow tool, Ptolemy, that you might know, you might have heard of it. It's like Simulink, if you never heard of Ptolemy. So you can, with our system, it's called Disegno, you can design an ontology to represent the underlying system. You can design some rules that must be applied to the data in the system, and then our Disegno compiles them into what we call a diagnostic decision server, okay? Which collects the data from the fields, applies the rules, and gives you the answer, putting them back into the ontology. Okay? So it can work, and we had some success with it. But don't try to use ontologies, at least in my opinion, to reason about the system. Okay, next topic. Here I said predictability of autonomous systems, and I think the talk that we heard this morning was very clear about the reason for doing this. Now, for instance, iCub is not going to be marketed anytime soon, I guess, but if it were, it wouldn't meet a certification process. Okay? That's it. Not because of electrical, mechanical reasons, maybe also for those because all these exposed joints are not very good, okay, in terms of mechanical certification. So you can pinch your fingers, you can have your air go inside these parts, so it's not probably going to work, but it's definitely not going to work on the software side. Not because it doesn't work, the robot itself is a perfect and very cute lab prototype, but it doesn't currently meet a certification guideline, okay? The title, it's small, so I will read it for you. Robots and robotic devices, safety requirements for non-industrial robots, non-medical personal care robots. Okay, so there's an ISO norm that disciplines this kind of robot. These are not industrial, non-healthcare. These are the robots that are supposed to be serving you drinks, okay, or mopping your floor, okay. And this norm makes a provision for safe autonomous actions. The norm also gives you suggestions on how to implement them, and the suggestion is remove autonomy, essentially. I'm oversimplifying here, but that's the point. So we don't want to remove autonomy. But clearly there's a conflict, and I would need 3 dimensions here, but I'm not very good with 3 dimensions. So it's adaptability, safety, and performance that are key here. Let's assume for a moment that performance is just fixed, okay? So you want to maintain a certain level of performance. Then you need to adapt. So you need to change your behavior in order to maintain performance because the environment is playing against you. But you need to be safe. And it's not by chance that adaptability is green and safety is red, okay? Because it's like green light and red light, liveness versus safety. I like motorbikes, okay? You might know so far that I do. Well, if I never drive my motorbike, then I'm perfectly safe, but I'm not happy, okay? Same thing here, okay? And clearly there's a trade-off. The more you drive a motorbike, the more you expose yourself to the risk of having an accident. The less you do it, the less you're happy. So how do you will probably travel this kind of frontier, and the goal of our research is to try and push this frontier up. So try to be adaptable and safe at this time. How? Formal methods, again, right? So inside this huge area of predictability of autonomous system of robots, okay, which it's very close, in fact. One of the things that you observe is that robots use machine learning a lot, okay? Now it's because machine learning became fashionable again. But in fact, machine learning has been there for quite some time. And no one in the machine learning community ever asked the question, or if they did it softly, you couldn't quite hear them. What about certifying our models? Okay, what about ensuring that the neural net emits a prediction which doesn't break some rules? And I'm talking about a trained neural net, because I guess everybody knows at least the basics of neural networks. Here I'm talking about the simple ones, the textbook ones, okay? So those with the input layer, one single activation layer with nonlinear functions, and output layer. So you want to approximate some function, you have data points, okay? And you have perhaps some very simple safety threshold that you don't want to exceed. Okay, so you can be safe but not accurate, right? You never match the function, but you never exceed the upper safety threshold. Or you can be accurate but not safe. This is by far the most interesting case for us, in the sense that your approximation of the function is good, but you fail to meet the safety requirement. And finally, you can be accurate and safe, which is our target. So how do you get to that? Well, what we did together with Luca back in 2010 was the following. Even if you consider feed-forward neural nets, okay, feed-forward means that data goes left to right, no recursion. Since neural networks have nonlinear transcendental activation functions, okay, if you transpose the correctness problem into logic, you get an undecidable problem. Undecidable means that you have no algorithmic ways of attacking it, which is bad because we like algorithmics. If you have recurrent neural networks, which are becoming fashionable again, it's even worse, because recurrent neural networks are Turing complete, demonstrably so, and so in that case you will need essentially software model checking. But it's undecidable, so you have no hope of having a conclusive decision procedure for that. Okay, so it's undecidable. What do? Well, we compute an abstraction. We over-approximate. We are looking for safety, right? So if the over-approximation is safe, so will be the concrete network. There's a Galois connection. There are technical bits and pieces that I'm not going into, but the idea is that you can do it, because once you have this abstract neural network, you can encode it into a Boolean combination of mathematical constraints. And what do we have here? Decision procedures, satisfiability modulo theory solvers, state-of-the-art procedures, initially meant for checking circuits, hardware circuits that do math, but also very good for this task. So they do the dirty work. We do the encoding, they do the dirty work. We managed to publish our idea, so it was a success according to the golden standard, the publisher perish that I mentioned before. It took us a little bit of work to convince people in computer-aided verification back in 2010 that neural networks was worth of attention. Today it wouldn't be the same, but 2010 was a little bit ahead of time. We also have a tool. This is a lot of perspiration from Luca, actually. I want to credit him for that, that verifies neural networks and is also capable to a certain extent to repair them, so to fix them if they are found to be wrong. And back then, we also did some experiment to see what were the boundaries. And unfortunately, we discovered, and this happens with formal verification, as I will say also at the end, we discovered that our procedure didn't scale very well. So we can handle small to medium-sized neural net, old-fashioned neural nets, okay, not deep neural networks, but then we stop, in the sense that the state of the art at the time was not helping us. So what happened? Well, we published our paper in 2010. These are the citations from Google Scholar. Then nobody noticed it, really. You can see. So it was like petals of flowers thrown in a canyon. You throw them and you hear nothing. But then eventually the flowers hit the bottom and we start hearing the echo. Now the echo might be fading out a little, but the paper is doing good. We are all very happy because the Italian system also takes into account citations for papers, so this is very good news for us. And what happened, okay? Well, as Professor San Giovanni Vincentelli said, fashion, right? The fashion is there. It's like humans. You have to live with it. So neural network, deep neural networks became fashionable. So in 2007, I guess, it was Emerson, Clark, and Szilard who won, Sifakis who won Turing Award for model checking. But last year it was Hinton, Benjo, and I can't remember the name of the third guy who won the Turing Award for deep neural networks. 2 words apart, right? I'm a fan of the first, as you may have noticed, but the good thing is that the neural network became fashionable, so our paper became interesting, and possibly they discovered that our methodology doesn't scale. Now, today, we are still researching into methods to make it work, but the interesting thing is that it was the machine learning guys that noticed that maybe something could be done about neural networks and something needed to be done about neural networks, okay? Well, fine, next. Still in robotics, okay? Still in autonomous systems. So neural networks is what you call supervised learning. You have a bunch of data are labeled, input, output, and you try to extrapolate from the data, not just fit it, extrapolate from the data. Reinforcement learning is the way we learn, right? As kids, you are an agent, you act in the world, you experience rewards or penalties, the stick and the carrot. It may be your parents, it may be the environment. Okay, you play with the cat scratches you, you know that you shouldn't be playing with the cat, you pet him, he purrs, you are happy, so you learn how to interact with the cat and many other things in life through this mechanism, okay? Reinforcement learning is anything but new, okay, for psychologists, operational researchers, engineers, AI. The book of the first edition of the Bible of reinforcement learning was written in 1998 by Sutton and Barto. Now they have a second edition. So by 1998, 20 years ago, unfortunately, the topic was already well established. But nobody cared, okay, almost. But then, deep learning, okay, let's take deep learning and apply it to reinforcement learning, okay, and then, voila, reinforcement learning fashionable again. The image you're seeing there is Professor San Giovanni Vincentelli was talking about Deep Blue versus Kasparov, right? Those days are gone. Now we know that the champions of the world of chess are programs, okay? And in fact, meet Stockfish. He's been 3 times the world champions of chess playing programs. Undefeated and undefeatable possibly by any human player, based on good old AI. Means alpha beta pruning, search, heuristics, recording of game playings, and so on and so forth. So Stockfish is a program that we built that by far surpasses our ability, but we control. AlphaZero is a different beast. AlphaZero was built in a lab by having it play against other computerized players and then against itself. Okay? Through an reinforcement learning mechanism. Result, in 2017 they played an epic match, 1,000 games, you know, computers are quick, 72 draws, 28 for alpha 0. So let's say an inductively raised intelligence was better, has proved to be better than a programmed intelligence. Okay? So this might be disturbing. For me, it means, when the game gets tough, the tough get going. So it's an opportunity for us because, okay, we have yet another program, this time a self-programmed program that may do bad things. Going back to robotics, in chess games you don't hurt each other, right? Unless you start throwing pieces, but this would happen only if you play with humans and they get angry. Computers don't do that. But if you are in a robot, then what does it mean to learn something with reinforcement learning? You certainly remember, if you ever did, when you were riding your bicycle, okay, how many stumbles and how many falls you took, and even later on, till you could master the ability to ride the bicycle with confidence. And the point is that reinforcement learning is trial and error. It's the way it works, okay? Life is hard, no way. But what if the robot breaks before it ever reaches the goal? Now, as when you learn to ride a bicycle, someone like your father is holding you a little bit, or you put those little wheels on the back, or you start with the bikes without the pedals. Okay, so there are ways to simulate the learning task without actually running all the risks. And people do it all the time. So they learn the policies in the simulator and then they deploy them on the robot. Still, the policy that you learn on the simulator might not meet safety criteria. Okay, so what's the mathematical model behind reinforcement learning? Markov decision problems, okay? What is a Markov decision problem, in case you don't know? Well, here you have a simple example. It's a grid. There's a start, there's a target, there are holes, and the cells close to the holes are slippery. So if you go to the hole, you die. But if you go nearby the hole, you have a chance to slipping inside the hole, okay? And this is represented over here. So every action you take might be successful or not, depending on what the environment chooses for you. So you have always a chance. Now, if you add to this what we call a control policy, okay, so technically, formally, a mapping from state to actions, then for every state, I know what to do. So, for instance, I need to reach the target. If I'm here, then I go here. If I'm here, then I try to skip the slippery zone and I go down, okay? Now, if you take the Markov decision process and the policy and you combine them, voila, Markov chain. Again, a nice formal model with well-founded properties, but the nice thing here and the idea is that, okay, you can feed the Markov chain together with the property you want to verify, namely that the probability of falling in the holes is as low as you wish to be, into a probabilistic model checker. There are tools that do that, very good ones. And that's it. So this is how you verify a policy learned by reinforcement to make sure that it doesn't do anything bad. There are further details, what happens when you go to the robot, you need to do monitoring and so on and so forth. I'm skipping those. Like the neural nets, not only we are able to prove that a policy is correct, but when we find it not correct, we can fix it to a certain extent. We cannot fix the environment, but we can fix the policy. We had the method for doing this, and then we applied it to some experiments in robotics, and we are still working on it, because the main limitation of this work is that we dealt with what is called tabular reinforcement learning, old-fashioned reinforcement learning, where you store your knowledge about the environment in a big matrix. But when the environment becomes really big, curse of dimensionality, you can't afford the matrix anymore, you need a neural network. And now somehow you need to combine what we did with neural networks, what we are doing with neural networks, together with what you're doing with reinforcement learning. And this is an open area for research as far as I know. Still robotics. This is the scene taken from the RoboCup Logistic League. It's a game, but it's a game played by physical robots. So the environment is somewhat controlled. It's like Industry 4.0. Here you see many workstations. A robot has to go around the workstation, carry some components, and complete some task. Okay? And actually it's not a single robot, but it's a fleet. And I have to do it in prescribed time with a certain quality of service. Now, all this can be solved in heuristic terms, but why not trying to be more formal? And in particular, what we did is that a formal model of the domain can be produced using a language is called planning domain description language. It's a declarative language like logic programming with a formal semantics. And once you have your domain formalized in that language with all the constraints that you need to verify, you can crunch it and encode to a Boolean combination of mathematical constraints plus cost functions. This is called optimization modulo theory. It's relatively recent advancement over satisfiability modulo theory. You could do in other ways. You could use mixed integer linear programming if you are a fan of that. But the important point is that from a formalization, we have, again, our number crunching. And now we can prove that our schedules not only are good, but are also optimal in some sense. So the performance is maintained, not in the face of safety or adaptivity. A few papers also for this approach. Also, like reinforcement learning, the whole picture is more complex than that, okay? This was just the formal part. There's more to it involving monitoring and executability. But the essence, we got it. The talk before me talked about cybersecurity, SCADA system, yet another application. Now we are moving from robotics to critical infrastructure. So what is critical infrastructure? This is from the Department of Homeland Security, is whatever infrastructure, automated infrastructure, that if attacked, if compromised, can damage the well-being of a large portion of a society. So, water and wastewater, energy production and distribution, finance, logistics, food and agriculture, critical manufacturing, 16 of them, okay? Essentially, almost all the production activities we engage. With the world becoming more connected, cyber warfare is becoming a clear and present danger, just to be cinematic again. In Italy, 2 or 3 years ago, we funded our cyber warfare operation command. Unfortunately, like it always happens with the military, it's not just for defense, but it's also meant for offense. That's the way it goes. But the point is that every country is recognizing the threat. Stuxnet was one of the precursors. Even before then, Stuxnet, the Aurora generation test in 2007 showed in a dramatic way how you could obtain a kinetic impact by intervening on the cyber part of a system by blowing up a generator. Look up on YouTube Aurora generation test. You will see the generator literally blowing up to pieces. Okay, it's very impressive, and that was done without actually placing a bomb, okay, on the generator, but it was done only by having the software attach the generator to the net out of sync, to the electric net out of sync, and that exploded the generator. Okay, so it's an issue. Where did we focus? There's a property that you may have heard of it in your also. It applies to life. It's called resilience. Okay. There was also a talk a few days ago about resilience of system. So you have a system which is functioning at a stated level of performance. There's an attack, an adverse event. The system decreases its performance. A resilient system will eventually recover from that. A system which is not resilient will fail. And to a certain extent, there is no system which can resist whatever attack. Now think of Fukushima, okay? So there's a limit to the resilience of any system. But the point here is trying to be resilient in the face of a cyber attack. So how do you go about formalizing this problem? Well, in the end, and this was also the case in Stuxnet, everything in a control system goes back to the good old control theory book, the feedback loop, okay? So everything is about the feedback loop. And an attacker can intervene on the feedback loop in several ways. It can modify set points, it can modify the regulation parameters, or it can modify the state estimation, which is actually what happened with Stuxnet, okay? The controller was not reading the correct centrifuge speed, and so it was increasing the speed. Fine. We have it, right? No problem. No good results here, unfortunately. But the idea is, okay, let's take our refinery, okay, and model it as a hybrid automaton. Very nice formalism, okay? Discrete transitions to represent the working of digital circuits, and continuous flows in each mode, okay, in each discrete mode, in order to represent physical evolution. Great, no? Well, and then what next? Once you have your hybrid automaton, you can run a model checker. These are output from the Cora model checker, which is a system that runs in MATLAB, and you can go comparing reachable sets. So you can postulate an attack on some of the parameters, and you can see how much the reachable set inflates or exits from the safe region when you actually attack the system using the model checker. The more the system goes away from the safety zone, the less it is resilient. Very nice. Unfortunately, it doesn't work for a number of reasons that I will tell you right now. Reason number one, you don't have the model. Reason number two, even if you had the model, it would be too complex for the model checker. Reason number three, the mathematics, even if the first two were satisfied, the mathematics for doing this comparison of reachable set is not there. And it's not easy for hybrid systems. Okay? So it's really a problem where we hit our face on the floor. However, we wrote it in a paper. And then we went in another direction, which is essentially, okay, the system cannot be formalized, so we have a sort of a data-driven approach where we take some KPIs from the system, we manipulate them through some filtering, essentially, and we try to assess the resilience of the system. There is still some modeling there, okay, but it's really mostly, let's say, classical engineering jobs of taking data from the field, applying some measures, and displaying the results on some dashboard. We are still working on that, trying to improve on this step, but right now I didn't find a student crazy enough to go into trying this at home. Maybe in the future I will. Okay. Last but not least, computer automated design. So this is yet another area. This is not about a system which is already made, but a system that you are making, okay? What a nice thing when you are designing a system and you want your design process to be ethical, okay, to have it done by a computer. You ensure that the computer is ethical. It won't do, nasty tricks to make things work. The domain we are working in, it's elevators, okay? Elevators. Italy is the second largest, has the second largest number of installed elevators after China. I'm talking about absolute numbers. This is because we are lazy, okay? And in relative terms, we are the first in the world for number of installed elevators. Elevators are, you may think, okay, but come on, an elevator, an airplane, no? You should be looking at something a little bit more interesting. Elevators are pervasive, are getting connected, for condition-based maintenance purposes. So they're also becoming part of this cyber-physical thing. So if you stop all the elevators and stairways in a country, you will see. And you can do ARM, because if you disable the safety components on an elevator, you can still create issues. Okay? So this is more about design. So essentially what you want to avoid, imagine you're in a building and together with the other landlords, you ask for someone to build an elevator. In Italy, we always have to ask 3 times to 3 different firms, companies. So a company is honest and will design an elevator which is good, sturdy, and very expensive. A company is a little fishy, so they will propose you something that is not very nice, and yet another company maybe will go in between. Now it's your choice. Which one do you take? The problem is that the process that they followed in order to assemble the design is a heuristic at best, but not heuristic of the kind that we like in AI. Heuristic in the kind of rule of thumb things, okay? And also the price quote is kind of up in the air. So, on the other hand, if you manage to put the actual measurements, the regulation, that's what we do, and the components that you have inside an automated procedure, then you can get a number of projects, and then possibly you can choose the one that suits best your necessity. So for instance, you might prefer a wider door because you have some of your flatmates who's disabled, so needs a larger door, rather than a larger cabin, or some other trade-off, right? But all the projects will be guaranteed to meet ethical principles, okay? Our case study is elevator design, and the idea is heuristic approach, but not in the sense of rule of thumb, in the sense of heuristic search to the space of potential configurations, genetic algorithms, or application, again, to satisfiability modulus theory. The heuristic approach is essentially hard-coded, so we try to replicate the head of the engineer inside the code, whereas genetic algorithms and satisfiability modulo theory go through a formalization part, which involves essentially constraint programming. Okay, so this is yet another application, and also here some success story. We are still working on that, and we are going to launch a spin-off on this. We recently met with an elevator making company. They said, no, your software is very nice. Unfortunately, it goes exactly in the direction we don't want to go, because it gives power to the people who assemble elevator on their own to make good designs. And we don't want that to happen. So there is always some resistance to innovation, but we will see if we end up like Uber or better. Right, I'm getting to the conclusion. And sorry for keeping you away from the lunch, but Luca told me that I could go, I could use up my time, so I did it. Essentially, as you understood, I'm really a fan of formal methods, so my suggestion is you have to leave that, you have to try hard to come up with a formalization. Whatever domain you are dealing with, formalization is really the first step that you have to undergo. You choose the one you prefer, and then perhaps it's my task to follow, or Luca's task to follow with something that can live up to the expectation. But formalization is really the first step to any activity that we may think of, even if it's hard. Like in the movie, no? Live, die, repeat. Where are you going to die if you do not pay attention? I've been there already. I've seen the movie many times, like in Edge of Tomorrow. I've been killed several times by the beast, so I can tell you at least a few of the problems that you might meet. Pore integration is the first. So if you develop your model in some language, in some environment, and then this environment is not connected in a tight way to the formal part, possibly in an automated part. Think about what happens with design of circuits, right? You have your tool to design the circuit, to simulate, and then to compile it to RTL. That's, an example where we should be going to. Then, the guy scratching your head. You can have what you think it is a formal model. Like UML, I formalized my application with UML, nice. And what is the formal semantics of UML? Nobody knows, okay? And that's a problem, okay? Because without formal semantics, all the castle crumbles down like a house of cards, okay? So, formal semantics. This is something, right now we have a project with IIT. I'm insisting, you do not only have to give me, you want to use behavior trees? Fine, behavior trees. You want to use PDDL? Whatever. But what is the formal semantics? Because without that, if I'm proving properties, I have nothing in my hands, okay? Unless I have that. Think about C and Java, okay, as a comparison. Computational complexity. Life is NP hard, okay, in this world. Means that it is at least as hard as solving propositional satisfiability. No question about it. Computers are getting faster. Now we have voices of quantum computing doing even further breaks. So maybe the solution to our problems will come in the future. Right now is there because we have still Turing von Neumann machine, and we still didn't prove that P equals NP, okay, or the other way around. But computational complexity is an issue. So if you choose a language or an abstraction which is too expressive, you'll end up not being able to compute anything useful. And finally, but not least important, the dark side of the moon effect. What is it? Look, I have this wonderful model of my system, everything is in place, fine. And then what about this code? No, this is just some glue code that I put there, because it would be too difficult to put in the model. We change it at times. That's bad, okay? That's the dark side of the moon. When you see very beautiful models, and then there is this tiny little bit of code which tends to inflate across time, which tends to go out of control, and which makes the whole thing again crumble down like a castle of cards. Since I'm, as I said, a little bit crazy, I'm repeating the quest. Okay, in Edge of Tomorrow, in the end, they manage to destroy the Omega. So maybe I will manage someday. I don't know. But we have projects in collaboration with IIT where we are trying to essentially push these ideas of formalizing the deliberation of robots and then proving properties about it. We are helped because there's a huge European project called Robmosis, which in fact pushes a lot the idea that you should be model-based. Actually, the models that they have in Robmosis do not have formal semantics, so we need to adapt a bit. But we are working on it. We worked on it with the project Carve, and there's another project Scope to come. And there's another project, maybe in cooperation with the Department of Defense, where we may want to apply formal methods to improve the results obtained with graph-based models. Okay, and that's it. Thank you very much for your attention. I'll be around and at the social dinner, so I'm not running away, really. So you can ask me questions even afterwards. Thank you very much.
As you said, they are really complex, and modeling them, it's quite hard. So you have to do some abstractions, some approximations, and there are some parts that are, I mean, most parts are non-linear, so it could be difficult to model. And I'm saying that how much do you think that this, let's say, approach can be, let's say, applied in the near future to this kind of systems that are growing so much? Like we have, and as has been said, that we have these systems that are so large. We have many sensors, and this sensor can be like really complex, non-linear. So modeling them could be difficult. So do you think that? Of course, it depends on the kind of system, of course, but there is like a good way to approximate them that it can be actually worth using to for example, fault detection or other kind of analysis to these big systems.
Okay.
You spoke about elevators. I don't
Yes.
know how they are made. I imagine that there are some non-linear parts, or there are some other things that you have to approximate.
Yes. Well, actually, in the design, you simply have to match size constraints. So, and most of the norm is already there. So someone did the calculations for us. We need just to transfer that in the model. So it's slightly easier in that case. In general, what I see around, for instance, in the railway sector, there's a project going on at FBK in Trento where they are trying to substitute the old analog logic that still controls the Italian railway network, which has been testing around the year for 7, with digital logic. And this is a very slow process. It's not happening fast. They found a way to learn models from the circuit diagrams. Then they found a way to translate what was learned into a formal diagram that needs to be rechecked by the human engineer in the railway, in RFAE, in the Italian railways. Then from that model they are going to compile in a provably correct way the software that needs to run on the machines that actually run the system. Okay, so it's slow, it's painful, but it's necessary. This is my view. It still requires a lot of human intervention, but this means, like in cybersecurity, that there's a lot of opportunities for research, for jobs, because you cannot automate the penetration of a system, okay? So if you're talking penetration testing, companies that do it have ethical hackers that do it all the time, who love doing it and find vulnerabilities. So it's still human intensive. That for sure. But it's happening, and in my opinion, in particular for the kind of intelligences that Professor Carlucci Aiello was talking about, so intelligences that are really autonomous, maybe have free wills, we cannot really, it's like the 3 laws, we cannot avoid to build something into them that prevents bad things to happen, because we cannot do it by hand. And one last thing is what happens in systems today is that, for instance, model checking is not applicable to every kind of hardware or software. When model checking stops, testing starts. And even with testing, you can be very rigorous, at least in statistical terms, to ensure that the probability of failure of your system is below a certain threshold. And this is how airplanes fly, spacecraft are launched. So it's not all through formal methods, definitely. The problem is that testing is at stake when you have autonomy. Testing works well for classical engineered system. With autonomy, it's a big issue.
Okay, before I ask my question, I want really to congratulate you.
Thank you.
Fantastic. And I think that you understand why your talk has been music to my ear. Because
Given yours.
completely your vision about the importance of formal methods and the importance of having proofs before passing to a testing phase that's necessary in some cases, and so and so. So, yes, it was really a pleasure to listen to this presentation, and a pleasure to see the various applications you have been developing over the years. And the question, you say that AlphaZero has won a certain number of
28.
and then
72 draws.
70 draws. Fantastic. Does this mean that the neural networks have really won over the good old-fashioned AI, or is this result in some way explainable because of the nature of the game, a chessboard game?
Yes. So I'm going to give you a biased. I'm going to give you a biased answer because you know my.
I want to have the answer.
Right. Well, you know my background, so my answer is biased because of my background. So in my opinion, it's an achievement that we must confront with.
We commit suicide?
No, I don't think so, because in my opinion the only way to make these artifacts safe and explainable is through good old-fashioned AI.
Okay.
That's my opinion.
Yes. Okay. Yes. And maybe the combination of the two approaches.
Exactly. A sort of Tao.
Every time in AI the story has gone
This way, exactly.
Okay, so let's thank our speaker.
Grazie. 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 Ok.